Hello and welcome to the second video on diagnosing CICS VSE storage violation dumps. What I'm going to do today is walk you through effectively what is a real storage violation dump. I put the presentation material together showing you snippets of information from the dump. The reason for that is that the dumps are so big, it's just impossible to embed what you see in a formatted CICS dump. So I'm going to take you through the dump bit by bit and show you where you find the information that you need in order to begin the diagnosis of a storage violation. Now, I'm doing this in a VMX-Edit environment, which is where we do all our CICS VSE debugging. And VMX-Edit is a particularly good tool for looking at large files. If I had to do this using ICCF, I think I would probably retire immediately, because ICCF is really bad for working with large print files. So where do we start? Well, let's have a look at the first part of the dump itself. You can see at the top that it's nearly 850,000 lines in size, which gives you an idea of how big these printouts can be. And I've seen much bigger than that. I've seen storage violation dumps that are well over 1 million lines in size. Now, in the presentation material, I give you the info and a control statement that you need to produce a storage violation dump formatting. And you have these parameters. And what I'll be doing today is taking you through the domain formatting, showing you what is important and what is not. You'll find, as with any dump, that only a very small percentage of the dump is actually of use. The trick is to find out what's important and discard the rest. Firstly, what's a storage violation? Well, a storage violation in CICS is a storage overlay that CICS can actually detect, which implies that there are storage overlays that CICS can't detect, which is the case. In fact, you could be having storage overlays in your CICS job every day, and CICS isn't detecting them. Now, the storage violation check that CICS uses are not the only checks that can be put in place, and the presentation material will tell you about some of the CICS storage protection mechanisms and how they can be implemented. But what we're looking at here is an SM0102 Abend, which tells you that CICS has detected a storage violation. That SM0102 comes from the message DFH SM0102, and in there you'll find a code. The presentation material will tell you that there are 4 basic codes that you can get with a storage violation, 3 of which are associated with an SM0102, and the 4th one is an SM0103, which is a storage violation trap. We're looking at a problem associated with storage that belongs to a CICS task. I mean, that's a transaction that's running in CICS, but specifically here, it's a task where a task is an instance of a transaction. It's possible that I'll use the words transaction and task interchangeably. You run transactions in CICS, but you could have 100 copies of a transaction called ABCD running at the same time, and they have to be uniquely identified. So when a new transaction is started, its transaction ID is associated with a transaction number, or task ID is another way that I'll use to describe it. So here we're looking at storage violation. A storage violation is an overlay that CICS is able to detect. When you run a transaction in CICS, the storage that it uses is dynamically acquired when the transaction starts, and you get what is called task-related storage. That is acquired for the task by using a CICS getMain. When that getMain is handled by CICS, it looks at how much storage has been requested, rounds that to a multiple of 16 bytes, and then adds another 16 bytes. These additional 16 bytes that are added are 8 bytes at the beginning of the storage allocation and 8 bytes at the end of the allocation. And what is put in here is something that's called a storage check zone, or SCZ, sometimes known as a storage accounting area, or SAA. And these act as little tripwires. It is not difficult to modify storage that you're not supposed to modify. And these tripwires are set up with constant values by CICS at the time of the getMain. They contain the transaction number and an alpha character at the beginning that identifies the class of storage. And as we'll see later, there are 4 classes of storage. 2 of them are below the line storage, and the other 2 are above the line storage. If those storage areas are overlaid, they're changed from what is essentially a constant value. When the storage is free-mained, CICS notices, and that is where a storage violation comes from. So a storage violation is a detectable overlay such that if the program code modifies the beginning or trailing checkzone, CICS will react with a storage violation Abend, which is our SM0102. It is typically detected on the free main of the storage, and that can actually be a long way away from where the damage occurred. And that's the basic problem with storage violations. CICS is able to tell you've got a problem, but it can't tell you when it occurred. And to make it worse, the most common storage violation that we see is with a code of 0F0C, which is when the transaction is finally terminating. And so there can be literally a huge gap in time between when the storage was overlaid and when it was found. If you open a case with IBM, you need to send us the unformatted dump. Please don't send us formatted dumps. We can format them. And we need the unformatted dump to look at storage that does not exist in the formatted dump. The 0F0C Abend, we can use the dump to get some basic diagnostic information that we can pass to you but it's highly unusual that we can solve the storage violation. All we can do is point you at a program or a series of programs perhaps, and say it looks like something went wrong in this bit of storage, possibly somewhere between here and there. Now, customer, you need to go away and look at the application program or programs and determine why the storage has been overlaid. Although it's possible, it is generally unlikely that this storage violation is be caused by CICS or any of the vendor non-application software. There is no point asking if there are PTFs to cover this situation because we have no known instances of bugs in CICS that cause a storage violation. 99% of the time, I estimate it will be a customer application program error or a vendor application program error. So, where do we start with the dump? Well, this is where I start. The code in the DFHSM0102 message is a trace point ID, 0F0C, and that trace point ID is associated with the SM or storage manager domain. Trace point IDs, which are 4 hex digits, are not unique except in the contents of the domain. So if I look for a character string which is SM space 0F0C, that will take me to a trace entry that will tell me more about what CICS has detected. In the DFHPD 430 data string, you were asked to format TR equals 3. TR equals 3 comprises TR equals 1, which is the abbreviated trace that we're looking at here. And TR equals 2 is the full trace, which you can see beginning here. The abbreviated trace is useful for giving you a 30,000-foot view of what's happening in the CICS system at the time, or precisely what's happening now and what happened just before that. CICS trace data is absolutely vital for solving just about every type of CICS system problem. If you disable trace in your CICS system, then you or I will have great trouble finding out what's going wrong. So you should be having internal trace activated or active all the time, and we recommend that you have an internal trace table size of at least 4096K in order to capture a decent amount of information. In some cases, we will ask you to allocate more than that. But anyway, here's abbreviated trace if you haven't seen it before. You have one line for each trace entry, and as it says, it's abbreviated. The amount of data that can be logged for each trace entry can be up to 4096 bytes. It can be a huge amount of information. So on the left-hand side, we have the task number or the transaction number or transaction ID. Sorry, task ID. XM. XM is the transaction manager, and it's the component of CICS that cuts in to start to run a transaction, and it's the code that comes in right at the end to close everything down. And what it's doing at this point in time is getting rid of storage that hasn't been explicitly free-mained. And as I said a couple of minutes ago, storage violations are typically detected on the free main. So ignore the one. SM is the storage manager domain. 0F0C is the code we saw earlier. SMAR is the name of the CICS module, DFH SMAR. Big deal. And what we have here is the type of trace entry generally. *exe* is an exception trace entry. CICS creates exception trace entries when it finds that there are things that are not quite as they should be. And by not quite as good as they should be, that could be simply you're reading a vSAN file and find that the record's not there, or they could be exceptions that relate to conditions that are so severe that CICS will now decide to shut down. What we have here is an exception condition that's somewhere between the two. It's not trivial, and it's not enough to normally shut the CICS system down. However, I mustn't forget that you can actually set CICS up so that if it detects a storage violation, it will shut CICS itself down. Although it's not common for that to happen. It's a bit of a bit too severe an action, I believe. Anyway, so it's an exception entry. Now, these exception entries are special cases in CICS. You can turn internal trace completely off and not allow CICS to trace anything at all. Well, actually, you can't turn internal trace completely off. Even if you said, I don't want internal trace active, CICS will always log exception trace entries so that if nothing else, in the dump, you can see what it was that CICS objected to. In real terms, an exception trace entry on its own is possibly not enough to diagnose the problem. You're slightly better off with a storage violation, but keep internal trace active. It makes a lot of sense. So what it's saying here, well, we're running a task which we don't know its ID at the moment, or the number. We don't know what transaction ID this is either. But what it's telling us is that it's failed at the storage check, which is the check for the SCZ values, has failed at this address. So this is a storage allocation that's been compromised. And let me take a note of that. And let me start logging some information. So the initial analysis of a storage violation dump, which is what the course, the presentation is all about, requires you to go through the dump and provide a series of clues as to why CICS objected to it, which program, which transaction caused the problem. You will not be able to find the actual instruction that did it. What you have to do is assemble a series of, if you like, jigsaw puzzle pieces. And when you've got all the pieces together, hopefully you'll have something that resembles a picture of what the overall problem is. But just like the case where this is a jigsaw puzzle that you've lost pieces from over the years, and you've also lost the lid that tells you what the whole thing looks like, you end up with a very partial picture of what's the problem. So the analysis will give you some pointers as to what has gone wrong, but it will not be a definitive explanation. And that is what you're stuck with in terms of storage violation analysis. It's just the way thing is. So I'm going to write a series of clues that describe what the problem is. I mean, if you have ever played the game of Cluedo, then what we're going to find is that there's Miss Scarlet in the library with the candlestick, sort of. So that's our first clue. Which storage allocation has got the problem? If you were to look at that address in the dump, what you should find is an 8-byte SCZ. And somewhere further on, there should be another SCZ that is at the end of the allocation. At the moment, this address is the beginning of the allocation. We'll actually see the storage that's there in a minute. So that's our first clue. What is the failing storage address? Okay. I'm not going to go into any more of the trace data here. We'll come back to that later. But apart from the fact that this is where it stops, and this is where CICS is setting itself up to take the SMO102 Abend and hopefully a dump. If you don't get a dump out of this, perhaps the dump has been suppressed, then you're not going to get very far in all probability. Well, you're not. It's quite simple. You won't get very far. You won't be able to diagnose it. Okay, that's in the abbreviated trace. Now, let's have a look at the full trace. There's a second occurrence of that domain and entry number. And here's the full trace. I think if you look at that, you can see what the difference is between abbreviated and full. A single trace entry has a maximum size of fractionally under 4K. And an awful lot of information can be logged in a 4K trace entry. The full trace will look at all the data values and it will format exactly what CICS has recorded. If you want to know what the content is of each trace entry, you will need to locate the CICS trace entries manual, which is effectively at release CICS-TS for VSE ESA 1.1.0. The base publication was never updated as a whole. You will find that there are enhancements guides for CICS-TS 1.1.1, 2.1 and 2.2. And what these manuals will have are additions and corrections to the initial trace entries manual. Each trace record will have a series of data values passed to it. Data value 1, you'll find, is completely uninteresting in just about every problem. The trace entries manual will say something meaningless like this is a parameter list, and the only people who can make sense of the parameter list are us in CICS support. We can look up the code and find out what the content of it is, but to be honest, most of the time it's of no consequence. Data 2 here. Now I've added the comment here. This is not formatted by CICS. I've added the comment to remind me what it's there for. In CICS level 3 support, we don't generally handle storage violations. They're normally handled by CICS level 2 support. because they are not typically CICS code problems. CICS level 2 support, in theory, should be able to handle any problem that doesn't require analysis of the code, which is where level 3 support comes in. That's not to say that CICS level 3 support will never look at storage violations, because there are some storage violations or overlays in CICS that will require level 3 support to have a look at, and maybe code something like a DFH trap that will be able to look at storage as CICS is running and take it up when it finds something strange. DFH trap is a program that is called when it's enabled at the time that every trace entry is produced. So we can write code that is activated and run for every trace entry, and we can decide for each trace entry whether to do some checking or not in CICS. Those are for the problems that are not easily solvable. For example, if some piece of code overlays a CICS control block and CICS takes exception to it, we would write a DFH trap to see if we could spot when the modification was made and take an appropriate dump at that point in time. For storage overlays, what you want is a dump that is as close as possible to the point at which the overlay occurred. If the dump is delayed too long, it gets exponentially more difficult to find the problem. The storage violation trap, which is something that we may ask you to enable, or you might decide to enable, and that's documented in the presentation material, aims to get the dump produced closer to the point at which the error occurs. Now, earlier I said that the storage violation is detected on the free main whenever that happens to be. Now, the storage violation trap increases the frequency of the checking. Every time there's an exec CICS request, on entry to the exec interface program, EIP, a storage violation check is made. Now, that storage violation check can be to the allocations for the active task, or it can be to the allocations for every task, depending on what level of storage violation check you need to enable. Both of them add overhead, but the trap that causes all allocations to be looked at on entry to EIP obviously has a much higher overhead, although sometimes you may find that you need it. The presentation material will tell you that if you enable the checking of just the current task storage, you can get a false positive. If you enable the checking of every task storage or all tasks, that can increase your response times quite noticeably. But if you need to find the storage violation, you need to find it, and you'll just have to cope with the fact that response times are going to be degraded to some extent. Anyway, enough of that. What's it actually telling us? Well, data 2 is the failing allocation start address, 2228 Charlie 120, which is what we got already. Okay, we know that. Big deal. How big was it? Well, the allocation was hex 1000 bytes long. Oops. Okay, it's not a jigsaw puzzle piece. Data 4, up to 512 bytes from the allocation starts. So what we're looking at here is this address, although we can't see it, but that's the address in storage we're looking at. So what we should have here is one of these SCZ, which is 8 bytes. Now, I know that that's wrong, but I'm used to looking at it. Let's have a look to see if we can find what it should contain. Oh, here's an interesting data 5, up to 512 bytes from the allocation end. So this bit here is 512 bytes before the allocation end. And if we go to the last line and the last 8 bytes, there's a storage checksum in hex, and here's the storage checksum in character. So what you have here is the transaction number or task ID 02658. So let's add that to our list of symptoms. Let's put it in the right place. That's another bit of our jigsaw puzzle. What we'll be able to do later is actually connect that to the transaction ID that's being run. That will come a bit later. Okay. So that's the trailing checksum. And what you have here is the class of storage. Now, I know, and it's in the presentation material, that says it's user key storage that's in 31-bit DSA or eDSA. The 4 classes of storage are user, user key 31-bit, which begins with a U. B is user 24-bit storage, that is below the 16 meg line. C is CICS key 31-bit, that's above the line, and M is CICS key 24-bit. Now the presentation material tells you a little bit about the what the difference is between CICS key and user key, and storage that is associated with a task in one way or another is or associated with CICS control blocks, for example. It's classified as being in CICS key storage or user key storage, and the segregation is performed to enable CICS storage protection to work. CICS storage protection basically says that the storage attribute is either CICS, so it belongs to programs running in CICS key, or it belongs to user key, programs running in user key. User key programs are not allowed by the hardware to modify CICS key storage, whereas programs running in CICS key can modify CICS key storage and user key storage. So the idea here is that when CICS storage protection is active, the average application program running in user key can't walk over CICS storage and bring CICS down. That's it in 30 seconds. So here's the storage checksum right at the end, as we expect. And if we go back to the beginning of the allocation, you'll find that is where the problem is. Okay, so that should have said U 0002658, and we've lost the first 6 bytes of the leading checksum. So that's the leading checksum, and down here we have the trailing checksum. So what's here is what CICS is complaining about. Chances are that the code that was updating the allocation prior to this address has somehow walked over the end and overlaid this storage allocation. So I would say actually this storage allocation is the victim in the storage overlay. On the right hand side, as per normal, the hex values are formatted in EBCDIC where possible, and special characters with dots or just spaces. And what you see here is this is an LE eye catcher. So this is LE stack storage. So it depending on the language you're working with, that is either storage for CICS, for LE code, or it could be storage for PL1 or C programs, actually declared storage. So we can add another clue. The leading storage checkzone has been overlaid. That's probably because the task that owned the previous allocation has addressed past so if the leading checkzone has been overlaid, the task that owned the storage prior to that point in time is probably the culprit. If the trailing checkzone has been overlaid, chances are it's the task that owns that particular allocation that's caused the problem. Now, the storage allocation before this one actually might belong to a completely different task. And we can actually find that information in the dump should we need to do that. Okay, so we got another clue. What else have we got here? Let's data 6. Up to 1K bytes before the start of the allocation. So this is the previous allocation, and this is the end of it. Okay, so it goes to the end address of the previous allocation and then formats up to 1K before that, depending on the size of the allocation. If the allocation is not 1K, you don't get a K. So here we have the trailing checkzone of the previous allocation. And as you can see, it's been overlaid. Now, at this point in time, we don't know which task owns that, but we can find that out information out later. In this particular case, this allocation is owned by the same task. So we can add another bit of jigsaw puzzle. The trailing checkzone, SCZ, of the previous allocation has been overlaid. So whoever owned that bit of storage could be the program that caused the damage. Now, while we're here, let's have a look at the formatted dump to see whether there are any clues as to the use of that storage. Now, if you look here, you'll find that certain strings repeat, requested record not found, another one here, record not found, requested record not found. What's possible here is that we've got an array of error messages. And what's happened that the program has been building the array and didn't stop when it got to the end. Oh, and here we got more. So the probability here is that the program code has been logging these error messages, but hasn't stopped when it got to the end of the array that was allocated for it. So let's add that to the list of clues. Is the problem due to an array of error messages is the problem due to a program incorrectly handling an array of error messages? And then up to 1K bytes. Oh, let's change that. Just save that. Up to 1K, but after the allocation ends. So this is the allocation following the one for which the storage violation was reported. And if you can see here, this is a valid SCZ. So this looks like okay, except what have we got here? Requested record not found. So this one looks good. And that's basically it. I don't think there's anything interesting there. No. So to summarize where we got to so far, I mean, if I wasn't talking and doing this, we'd have got all this information in a much shorter amount of time. So what have we found? Well, we know which storage allocation was the one that CICS objected to. We know it was 4K bytes long. We know it belonged to task ID 02658, but we don't know what the transaction ID is yet. Once you can identify the transaction ID, you have a better idea of which program or which programs are involved in this problem. I mean, it could be the case it's one program, or it could be 100. It depends on the complexity of the transaction. If you've got enough time, you can work your way through the trace, going backwards from the point of the storage violation and figure out which programs were running. But that can take an awful lot of time, and you have to bear in mind that the trace data may not include the whole of the trace activity for the task that found the problem. It could be that your trace table just wasn't big enough, which is why we suggest that you have at least 4 meg of storage allocated to the trace. If you've got complex programs, you might want 10 meg or more in order to capture all the trace for that particular task, or more. How big? Well, how is a piece of string question. It depends. Okay, so we've been able to identify quite a lot of information from the trace data itself. But let's go back over the dump component by component, domain by domain, to show you what information is potentially of interest. AP domain, application program domain. The application program domain is able to convert a transaction number or task ID to a transaction ID. Now, we had transaction number 02658, and oh, that's a shame. It's not in the list. The problem we have with a 0F0C code Abend is that the application program is terminating, and at the time it finds a storage violation, all knowledge in the AP domain has been deleted. So we can't use the AP equals 1 information to find our transaction ID. Not a problem, because we can find it somewhere else, and I'll show you that later. Okay, that's AP equals 1. This is the AP equals 2 part, which is application domain control blocks. Well, it's actually a bit more than that. It's not only the control blocks, but you have the allocations for each task formatted here in dump format. Okay, the control blocks that are formatted here, I'm not going to talk about those because they're not relevant to solving this particular type of dump. And in fact, these are actually part of other storage allocations that we'll see later. Let's go forwards. These are the storage allocations. This is the class of allocation. So it's CICS key storage. That's 31-bit. 31-bit CICS key storage. Here's the SCZ, which is task number 4. And the C3 is the C. That's the 31-bit CICS. And here's the trailing SCZ. As this part is being formatted, the CICS trace format, as the CICS dump formatter, DFHPD430, will check all of these SCZ values. And if it finds that they've been overlaid, it will write a DFHPD0124 message for the leading check zone and a PD0125 for the trailing check zone here. Let's see if we got any. DFHPD012 something or other. Oh, no. We haven't got an 0124 or 0125. Now, we know we've got a storage violation because CICS has told us, but we can't actually see it being identified. Again, code 0F0C, by the time CICS has found that, all information in the AP domain has been lost. So you won't see AP equals 2 formatting giving you the overlays, the storage violations, the DFHPD 0124, 0125 messages. It's not to say that you'll never find them. If that's the case, then your storage violations are a bit more pervasive than you thought. But the dumps you get with the other codes, you'll definitely find the 0124, 0125 messages telling you that the leading and or trailing check zones have been overlaid. So You can get in the AP equals 2 output, you can get to see how big a problem it is. Is it just one allocation, or have multiple allocations been hit? Maybe CICS has only just noticed one of them. I'm going to go forward a little bit further. Let's see if I can find something that's a bit more interesting. Well, sort of interesting. The presentation material says that on 2 slides, it provides how to quickly find interesting bits of the dump. And if you want to find storage for a particular transaction number or task ID, then look for dot and then the task ID. Okay, so if you're in ICCF, then that's a quick way to find something for a particular task. Now, we won't get any storage for the task that had the problem in AP equals 2 because it's too late. The SM0C full trace entry will give you some of it. If you want to get any more, then you'll have to print off parts of the dump using info and a print address range. When we look at the dump, it's a lot easier because if we got a storage address, we can just browse it interactively using a CMS, a dump browser. That's in IBM internal use only. Okay, so AP domain, we can possibly convert the transaction number to a transaction ID, except for this dump. And in the TR equals 2 part, we can find all the storage active task related storage allocations, and CICS may actually ID some allocations where the SEZ have been corrupted. Now, it's all very well looking at the application domain, but there are lots of domains being formatted here. How do you know what's where? Well, this is where the magic of xedit comes in. I'm going to ask it to find all occurrences of 2 equals sign. And what that will do is give us a sort of high-level view of the content of the formatted dump. The formatter uses equals, 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 then the domain ID to tell you where things start, and then subsections of that may contain another 3 equals sign or 2 equals sign. Okay, so this is the power of xedit. It enables you to compress the formatted dump so that you can quickly find the main locations that you're interested in. So we looked at the AP domain initially because that's always first. Now we're going to look at the loader domain. The bit that I'm interested in, the loader domain, is actually not the beginning. It's actually the program storage map. So let's locate that and show all occurrences. What you have here is a list of all the programs managed by CICS that have been loaded. And that is formatted by ascending storage address. Now, here you've got some 24-bit code, and later on you'll find 31-bit code. But this is sorted on ascending load point address. Now, the load point is the virtual storage address of where the phase has been loaded. The entry point over here is the address of the first instruction that will gain control when the program is invoked, bearing in mind that a presence of a high order 8-bit says that this code is 31-bit enabled. So the actual entry point address will be obtained by removing the 8 bits. In that case, it's nice and simple. So the entry point address is 180 Charlie 38, and the low point is 180 Charlie 38. Okay, nice and easy. Let's get rid of that change. This is LE. This is LE. This is LE. This is CICS. And oh, this looks like a non-CICS program. I've no idea what the program is. All I know is it's been loaded at that address and the entry point is the same as that address. Oh, that's 24-bit code. That's running in 24-bit mode because there's no 8 there. This is the name of the program. And CICS DFHYA 430. Oh, this is the exec interface stub. So although the program has been loaded at that address, the actual start of the primary application program is here at 9020, because the exec interface stub that's linked at the beginning of the phase is hex 20 bytes long. And what we know here, this is the exec interface stub, so we know that this program has been linked in VSE 6.2. 430 is the internal release number for CICS for ZVSE 2.2. If that said 420, that is CICS for ZVSE 2.1. And if it said 410, that is CICS 1.1.1. And you can get lower releases. I mean, I've seen CICS VSE code in here that's been linked for CICS VSE execution. So user application programs will have a CICS name that is typically the stub. And although that's the load point address for the phase, the customer code will actually start hex 20 further on. Again, I'll just get rid of that modification. I don't want to hold that permanently. Now, why am I bothering to tell you this? Well, what we'll see later is that for most exec CICS commands that are traced, it'll give you a return address to the instruction after the one that called the exec interface program to be called. For those of you with assembler knowledge, the trace entry will contain the value in register 14 at the time the exec CICS request actually actioned. So it's the return address to the application. If you want to find out where in the application program the exec CICS command was requested, if you find the return address from the trace entry, find the next lower load point address, subtract the load point from the register 14 return address, it'll give you an offset in the phase. If you then subtract hex 20 from that, it'll give you an offset in the program, the primary program. If it's more than a single primary program, you'll probably want to have a look at the linkage editor map to figure out how this all maps in terms of modules. But essentially, it will give you, from the trace entry, you can find a program name and then a hex offset in the phase, or hex offset into the primary module, depending on how you want to run the maths. That's why we're looking here. I'll show you that later. Let's go back to our list of domains. Whoops, let's try typing that properly. You'll notice that whatever order you specify the domain formatting, it always prints them in an ascending order based on the domain ID. So there's the loader domain. PG domain. What are we interested in here? Well, what we're interested in here is something called the PTA summary. I'm not even sure what PTA means as an acronym. All I know is that I go here for certain things. Let's have a look, see if we can find anything interesting. It's a bit hard sometimes for me to remember what's interesting and what's not. PTA summary for Tran num 38522. Let's have a look there, see if there's anything interesting. Not so much. The PTA summary gives you an idea of the programs that were involved with a particular task and obviously with a related transaction. What we have here is the logical level. This is the link level. Yeah, if you're familiar with CICS, you know that when you execute a transaction, it starts the first program. That program can perform an exec CICS link to another program, and then you have a second level of link. That second program can issue another link, which takes you to a third link level. So this is the logical or the link level. Task ID 22168 is currently at link level 1 running this program, which is a VSE program. And it provides a bit of information about it as well. If you find that the task that you're looking at here is the one that had the storage violation, and I don't know if we can find that here, it will very rapidly tell you which program was active at the time the storage violation occurred based on the current link level. Now, as it is, we've actually not we're going through task termination, so we don't know what the active program was. The first program that we were running unless that program had done an executable to another one. So it's not of much interest here, but the PTA summary will show you what link level you're at when the Abend occurred. What it will also do is if there's a COM area involved, it will give you the COM area address and it'll give you the COM area length. So you can find the COM area that was passed to a program. Let's see if there's anything of interest here. No, these are all CICS programs. Let's see if I can find a link level 2. I know there's a link level 2 here somewhere. It's just a case of finding it. Oh, there we are. Okay, so transaction number 19 is currently at link level 2. So when the transaction started, we were running in DFH AP ATT, and that has issued a link to DFH CXPA. So this is the active program at that particular point in time. Okay, so the PTA summary then can tell you what is the active program at the time the dump was produced. It can be rather difficult finding the active program from the trace. It's not impossible, and in fact, I've got a full trace analyzer, FTA, a Rex program that helps me find information an awful lot quicker. Okay, so that's the PG domain. The PG domain can be used to find out the active program when there's multiple link levels. And our task was 02658. No, it's gone. We don't have anything of interest here. It wouldn't be of interest anyway, because we got back to level 1 link anyway by this time. Okay, so that's the PG domain. The SM domain. Now, there's a lot of information in the SM domain, like the PG domain, but only some that is of interest to us, potentially. And it's the task subpool summary. Let's go there. Let's just hide some of these blank lines. Oops. When a transaction starts, it's allocated a unique transaction number, which is 5 digits. And at the time it starts, CICS assigns 4 task-related subpools. These are the names. Incidentally, these are the values that go in the SCZ. So what you have here is a subpool that is for CICS key 24-bit, CICS key 31-bit, user key 24-bit, and user key 31-bit. And each of these subpools acquires a series of pages. The number of pages ranges from 0 to potentially a big number. So this bit of the dump is actually quite useful in a short on storage, because you can see which guy has acquired a lot of storage, if that's your problem. Now, these particular entries are not of much use. Let's page forward a bit. Let's see if we can... there's our task. Let's go. Let's find a few more. Okay, so give you a decent picture of what's going on. Okay, so let's have a look at not out at the task that failed. Let's have a look at another task and see if we can give you a better idea of what's going on here. Okay, so task 2138. Now, as I said, each task subpool acquires a number of pages. The pages are either 4K in size for the first 3 subpools, or is 64K for the user 31-bit. So initially a subpool starts off with 0K, and in the first instance, CICS will grab a page's worth of storage and associate it with the subpool. It will start to use that storage, and then when it runs out, it will allocate another page or pages. So over time, each task will acquire a series of pages. The difference is that some of it is 4K page size, and one part of it is 64K page size. What you have in the column here is the amount of storage that is actually in use in those pages, which is normally less. Now, this does seem rather wasteful, but it's actually quite useful from a storage protection point of view, because rather than jumble up all the storage allocations so that they're together, the storage is allocated in unique 4K pages or 64K pages, which basically gives you a little bit of separation between that task's storage and other task storage. Okay, so you get a bit of unused storage, but you get an element of storage isolation. If we go and look at our task, which we can find here, you'll find there's only one subpool. What's happened is that XM has been tidying up the storage allocations that are still in place, and it's worked the way through the first three with no problem. And when it's got to the 31-bit user storage, that's when it's found the storage violation. So it's trying to free some of this, and that's gone badly. Okay, so what you can see here is how much storage from a page point of view is allocated to a particular task. Possibly more of interest in a short on storage, but nevertheless, potentially of interest in a storage violation. Part of the time that there are places in the dump that are of interest, and the rest of the time they may be not of interest. What I'm showing you here sort of generically is what parts of the dump might be of interest to you. So that's SM equals 1. Here's SM equals 2. Now, there's a lot of data formatted in SM equals 2, but what we're interested in here is these guys. If I can find them. SCE control blocks and SCF control blocks. CICS keeps track of every active allocation, get main allocation, and the SCE maps allocated storage. Here's the address and here's the length, and SCF contains the address and the length. Now, if we add these two together, you should find that comes to hex 1000. So these two control blocks here map out a 4K page starting here. The first hex 5C0 is allocated, and the last hex A40 is currently not in use. Again, why do you need to know about these? Well, it's one of those bits of information that you might need to know about in order to help you solve the problem. So if you need to find out which pages, what's in the page, where the pages are in storage, and what is allocated and what's not allocated, that might be important information to you in solving the storage violation. See if we can, let's use the right, see if we can find, oh, there we are. Forget the SCA, that's a high level control block. What we have here are the SCI and SCF control blocks for the task that had the storage violation. So again, what you can do here is you can map out what's allocated, where in storage. So if you want, you've got so many pages. If you want to know where all those pages exist in CICS storage, you can go here. So that's allocated, that's allocated, that's allocated, that's allocated, blah, 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 blah. And here's all the free areas. Sorry, that's an allocated area. Oops. So SCE and SCF, just to repeat myself again, enables you to map out which pages are where in storage and what part of those pages are free and what parts of those pages are allocated. For example, let's say that the storage violation was in an allocation at a particular address. If you can get the start address of the allocation, you can come to here and find out which task owns it. Now, it could be that the allocation that's been walked over doesn't actually belong to the task that's running. It could belong to another task. Anyway, so potentially another information source that is another clue for the jigsaw puzzle. I say potentially, it depends. Now let's go slightly out of sequence here. Let's go to the XM domain, Transaction Manager. Now, earlier I said that it would be nice to have the transaction ID. We couldn't get it from the AP domain because the task has effectively fallen out of the AP domain, and we're now in XM, Transaction Manager. Oops. Don't know what happened there. I must have typed something wrong. Sorry about that. Fat fingers. 02658. So the transaction ID we can now put in. So it's task 2658 transaction ID CPMI. Oh, this is probably associated with CTG. And CPMI is like a cover transaction for running the programs. So normally there's a link between the transaction ID and at least the first program. Here it's not quite so easy. Okay, but at least we know the track. Oh, that's interesting. We had a program check. Oh. Oh, it had a program check. That's interesting. When you have storage violations, you might find that you had a program check just before the storage violation Abend. Equally, it's possible to have a program check after the storage violation. Now, the program checks may be related or not related to the storage violation. Now, I know in this case, because I've had a look at the dump, that the program check that occurred was actually in a bit of LE code, CEE. code. And the reason that the LE code program checked was because the storage violation overlaid part of an LE control block. LE has the habit of allocating its control blocks in with the LE managed storage allocations, which is slightly dodgy because an error in an application program can not only modify the application storage, but it can actually walk over LE control block storage. So in this particular case, the storage violation overlaid a part of an LE control block, and LE took exception to it. CICS has a slightly different attitude towards storage management control blocks. CICS storage is managed as a series of DSAs with a maximum size of DSA lim and EDSA lim. Now, CICS is sensible, and none of the SM control blocks are allocated in the DSAs. They are all allocated in GetVis storage. That is not to say that they can never be overlaid, but the chances of overlaying an SM control block is a lot less than an LE control block. Going back to where I started on this, the ASRA might be an indication that some code has found the storage violation, or it could be that the ASRA is actually where the storage violation occurred. Something, the ASRA itself is an indication that something went wrong, and that's where the storage violation occurred, but you can't be absolutely sure. So it's worthwhile following up on any program checks that occurred just before the storage violation, not 5 minutes ago. You're talking of fractions of a second, and program checks that occurred after the storage violation, you may find that the storage violation itself caused the problem. In fact, if you get a storage violation, it is possible that you'll get subsequent storage violations. When you get multiple dumps, it's normally the first one that's of interest, rather than the latter ones. Anyway, that's that. Let's go back to the trace domain, and just a very quick look back at there. Right, internal traces started, good. 8 meg, that's very good. Now, trace is your friend. As I said earlier, even us in CICS support can have a huge amount of trouble diagnosing a problem without trace. CICS it's very complicated, and huge amounts of code, and it's very difficult to find out what's going on without trace. Now, we tend to look at trace day in, day out, and it's very verbose, but we've basically worked out a way to remove some of the CRUD and look at the entries that are useful. Now, from your point of view, you're probably interested in looking at what happens in exec CICS. So what I'm going to do here is show you what an exec CICS command looks like in trace. Here's the task ID transaction number, which is the one that we're had the storage violation for. Here we got domain, the AP domain, and this is the trace entry number within the AP domain. Now, this is the result of an exec CICS command. We've gone into DFHEIP, the exec interface program, and why we've gone on in there is this is the start of an exec CICS read. Now, if we go down, there's where you go back to the program. Okay, so APE1 entry is where we start handling an exec CICS, and AP E1 exit is where we come out. And on the exit, it gives you an idea of whether the command worked completely or not. What you have between there and there is what's going on, and you can see Tmon cutting in there to do some of its accounting. And there's a lot of reads going on here. Here we've got another read. And here we got another read. And oh, exception. This is the VSAM component of exec_CICS read. Exception, record not found, and on the exit you can see it's not found. Okay, so from your point of view, you can, if you can ignore all the crud between the APE1 entry and exit, you can get an idea happening at the application level. If you were to activate EI level 2 trace, you get something that approximated to a CDF trace as well. It's not active here, and that will give you a lot more information about the exec_CICS command. Very useful information. Okay, so you can relatively quickly look at the exec_CICS activity that preceded the Abend, bearing in mind there may be a huge amount. Now that's at the overview level. One of the problems that you have with going through the abbreviated trace, well, you can see how much trace data is being produced by the failing task, huge amounts. That is basically the problem with analyzing trace. There can be such a huge amount of information that it's quite difficult to picture what's going on. Massive, massive amounts of information here. Yeah, I've got a full trace analyzer Rex program that it enables me to get a much better picture of what's going on. Well, let's here's where the storage violation. Let's go backwards and see if we can find anything of interest here. So normally when you look at trace, you find the point of error, which is here, and then you work backwards to see what was going on before then. But in this case, there's an awful lot of activity. So we go 02658 TCP NXM. What's going on here? Oh, and there's another task 02683 getting in the way. So we can work backwards to a certain point, and then we find trace entry for another task, which makes things doubly difficult. Well, in the presentation material, I give you DFHPD 430 parameter that enables you to format the trace just for a specific task ID or transaction number. Arguably, that will make it easier to work backwards, finding out what's going on. Anyway, so what trace does is show you what was happening before, and from an application point of view, it's the exec_CICS commands that are possibly of interest. Now here's the full trace, and as we saw before, full trace formats a lot of information, and if you found abbreviated trace hard to decipher, well, you're into a completely different league here. Let's show you something that's potentially of interest. On the EIP entry, you have a field called RET. This is the return address. For the AP E1 entry and exit, this is the return address in storage to the instruction after the exec kicks. Let's just copy that and put it in here. Now, bearing in mind that if there's a high order 8-bit, that is just the machine saying that it's a 31-bit address that's being used. So if we take the 8 out of there, that becomes a 2. So that's a return address. I'm just going to make a note of where we are. I'm just going to give that line a label .a. This is where the program storage map comes into use. If you remember, I said what you have here is a list of all the programs and where they're loaded in storage. And from this, you can figure out which program, the return address, that's our return address, 22648472. We can actually find which program this is. (2264). Okay, 22648472. 226. Oh, there's the next higher one. So we have the return address is somewhere within that program. So that's the program. If we can find where that's loaded, which is here, let's find, oops, sorry. Need to find my trusty calculator. Okay, hex. So I'll do this the right way around. 22. Take this out of the way. Hope that's right. So the return address 2264. Excuse the beep from my laptop. It's telling me battery's getting low. So the return address is in phase EE 3001 plus 29472. Bearing in mind that the first hex 20 bytes is the stub, that's potentially 29452 into the main program, but equally it could be into a module that is linked in with the main program. So that's the phase offset. And you can take that to an appropriate linkage editor map to get an idea of which module is involved. Anyway, so there's a return address and how it can be used. So you can go to any APE1 and find a return address here. And where's the APE1 exit? Yeah, you got the same here. So you can trace an exec_kix command to a program phase name and phase offset. Pretty straightforward, but until you come to about 2,000 of them, and that takes an inordinate amount of time. My FTA Rex trace analyzer actually works that out for you. Can save you literally hours. Now, while we're here, something else of interest, potentially in some APE1 entries in the full trace, this address here sometimes works out as being the working storage address of the active program. It definitely is for assembler, DFHEISTUG. Sometimes it works out for other languages that is the start address of the COBOL working storage or pure one stack, and C I don't know because I don't write in C. So trace is your friend, but without the tools, it can take a lot of time to work through it. Somewhere around, I think. Yeah, what I've done. This is what the output of my FTA Rex code looks like. Oh, let's try. I hate Notepad. It always remembers the last direction. Oh, there we are. Yeah, this is what my FTA Rex code does. It finds the exec_kix commands. It tries to identify the name of the transaction. Unfortunately, because this wasn't in AP, it was one output. It doesn't know it, so it's unknown. So for each read, for each exec_kix command, it actually works its way through the loader domain from the trace domain and gives you program name plus offset. See if we can find. There's quite a few tasks running here. Ah, there we are. Try again. So this is the back end of the trace data for task 02658. So you can see that it's got to the end. It reckons it's decided that it's terminated. Well, it's almost terminated, but as good as. So it gives you the response time that it sees from the trace, the amount of time it's been dispatched. So 3/4 of the trace elapsed time is actually associated with the task that failed. And what was it doing before then? Well, it was going off to top secret to remove the security inside of things. And where was it? What was it doing before? Oh, it's in program error program. Bad. Yeah, it's done a link before that. So the advantage of my FTA is that it can summarize the trace activity. It will highlight useful trace entries, and it will show you things like links occurring, when waits occurring, or here's a transaction dump. So we got a transaction dump out of this, which is an awful lot of work. Trying to avoid transaction dumps, or in fact any dumps in CICS, unless you need them, unless you actually use them, because they can consume a huge amount of CICS resource. And even a transaction dump is potentially a huge hit in terms of performance. So you can see there was an awful lot going on in 2658 just before it decided to go bang. And here's all the activity that happened before then. So the storage violation occurred somewhere. Here we got the ASRA. This is LE going bang. So all that activity that you just saw was dump processing and what falls out from there. And what the task was doing before that point in time is all this. And somewhere in there was the storage violation. It's literally anybody's guess where that was. And you can see a massive amount of work. Well, I'm trying to, if you try and imagine doing this manually, you probably want to pass it on to somebody else. So that's FTA. CICS level 2 and CICS level 3 use that because it makes our life easier. Okay, so a rather depressing conclusion to this, but I told you at the beginning, this is not everyone walking off into the sunset happy ever after. Here's a real storage violation, and here's really how difficult it can be. And this is what we ended up with. We're running CPMI, which is probably running a whole series of programs. The storage violation occurred at this address, an allocation that was hex 4K long. The leading check zone had been overlaid, so it was probably an overlay in the previous storage allocation, which we found was actually belonged to the same task. And from the data we can see in the trace, it looks like the program's been building an array of error messages and has literally fallen off the end of the array and has corrupted the storage over there. So that's the best we can do, folks. We've got a little bit of information about it. It's time to hand that over to the applications people, and they can scratch their heads thinking about this. They might be able to find something, or they might not. Certainly from a CICS support point of view, this is where we stop. We can't go any further than this. We don't know the applications. We don't know the way they're supposed to work. We don't have the source code. It's over to you guys. If this was me reporting this, I would probably say something to the customer like, if you really want a better chance of diagnosing this, if you find the applications people get really stuck because this is a real tricky one, what I suggest you do is activate the storage violation trap, CSFE debug, comma, something. And if it happens again, what will occur next time is that the storage violation will be detected much closer to the point at which it occurs. The storage violation trap fires at the start of every exec CICS request processing in EIP, and it's checked again at the end of the EIP before transfer control back to the applications. And what you'll find, and it's documented in the presentation material, is you'll find an SMCK trace entry, well, entry trace, let's get that right, SMCK, which is the DFH SMCK storage violation track code. That will occur just before you get the storage violation event for an SM0103. So at that point in time, CICS has detected the error. Now, if you go back in the trace to the first occurrence of the SMCK exit trace for that task, that is the last known point in time in that task when the storage was known to be valid. So somewhere between that point, and you'll find the EIP exit, which will give you a return to the program, that's the last known point in your code when the storage was good. Somewhere between that exec-CICS command completing and the next exec-CICS command starting is where the damage was occurred. So instead of having potentially thousands of trace entries to work through, you've maybe got a few tens. In fact, you've actually got two. EIP entry, go back to the EIP exit. So you trace that back to the program. What was the program name and offset? Well, between that and the next SMCK is where the damage occurs. So you are isolating the problem to a lot less code, but it still will not finger the actual instruction. It will say it occurred somewhere between now and previous exec-CICS. And that's the best you're going to get. Okay, well, this is showing you the worst possible case. If you find that it looks difficult, well, welcome to our world. Yeah, CICS, Abends can be difficult to diagnose. Well, I'm done. I hope this has been of interest to you. I'm going to stop talking now. And I hope that all your storage violations are easy ones. Bye for now.